Okay, in this video, we're going to introduce the idea of electric charge, something I think most people have heard of, and even understand maybe even a few of the basic rules, but we're going to go much deeper with it and really just kind of reveal to you the secret nature of the world. This piece of paper, for example, is made of entirely of charged particles. And that's not obvious because it doesn't normally exhibit any of the behaviors that we would typically associate with charged objects. But it is made of charged objects, and we're gonna explore that very deeply. And you will see that all objects, including the air itself, is actually made of these little tiny charged particles. The electric charge is a physical property of matter. It's just something that they inherently have, like their mass. Not all matter has an electric charge. There are some particles who are not charged, but in general, if they are charged, then they will experience a force whenever they are exposed to an electric field, or if they are exposed to a magnetic field under the right conditions. Magnetic fields don't always exert forces on charged particles, but they are capable of it, and that's a very mysterious thing because it's invisible. It's not something that you can see. It's not like one charge reaches out to the other charge. Somehow, invisibly, they can communicate with each other and make the other one aware of the fact that they are there. Now, I'm sure that everyone is aware of the fact that there are two types of charge, both positive and negative. These were named by Ben Franklin. He's the one who coined the term. It's kind of unfortunate because, it would have been better if he had chosen something else. What I don't like about the idea of calling them positive or negative is because positive and negative has a mathematical meaning. There's a mathematical meaning to the word positive and negative, and we've been using it in physics all the time. Mostly we use the positive and negative to indicate the direction of something, but in this case, that positive or negative does not indicate anything about direction at all. In fact, we're going to ignore the positive or negative name here in terms of the direction, and I'll show you a different way that you can think about that as we go a little bit deeper into the topic. But for our purposes, whenever we see something is positive, we'll put a little positive sign in parentheses. If we see that it's negative, we'll put a little negative sign. And in order to indicate that something is neutral, we'll simply put a 0 in parentheses next to the object to indicate that that object is positively or negatively or neutral, meaning that it has no charge. Positive and negative are very much, this idea of it being a property of matter. It's kind of almost like an orientation, very much like the way your hands are, right? So my hands are right, and I have a right hand and a left hand. Okay. Now, when I look at other objects, I could describe them in terms of their handedness. So that would be similar to the way we describe things in terms of having mass or in terms of having electric charge. Electric charge is a little different than mass, though, because there's really only the one kind of mass, but there are two types of charges, and they behave in exactly the opposite way to each other. So, for example, I might say that this pen, I would not say is right-handed or left-handed. I would say this pen is neutral. This pen has no handedness. But other objects, like, for example, a baseball glove. Well, baseball gloves are very rarely neutral. They normally are designed to go on your right hand, or they're designed to go on your left hand. So some objects are handed, and other objects are not handed. In the same way that some objects are positively charged, some are negatively charged, and some of them are neutral. It's just a property of that object, the way that object is built and organized. Now, I'm sure that the interactions are actually probably pretty well instilled in your mind. Those interactions say that opposites attract. So that, for example, if I were to take a positively charged object, this object that I keep drawing, you'll see I'll be doing this a lot during the videos, is something called a pith ball. Pith ball is just a little small insulating material that is surrounded by some kind of conducting material. And I'll show you how to make one of these objects. It's a thing that you can put charge on it, and it will generally stay there for you while you do your experiments. So it's just a way of testing out things and seeing how they react and knowing that something is charged. If I bring a positive pith ball, that's spelled P-I-T-H, if I bring a positively charged pith ball near a negatively charged pith ball, then what I'm going to see is that they will begin to move towards each other. They will be attracted. It's as though somehow they know that the other one is there, even though they're not touching. They will experience, of course, an equal but opposite force, because that's what the third law says, that if this guy exerts a force on this positive charge, then this positive charge must exert the same force back on the negative charge. So the idea that opposites attract, I'm sure that's something that you're very familiar with. And then even the idea that like charges repel, it's not quite as catchy as the opposites attract. But ultimately, if I were to put a positive pith ball and then I brought another positive pith ball, what I would see is that they repel each other, that they also experience an equal but opposite force. But in this case now they begin to push away, like if you, for example, were to bring the north pole of two magnets together. I'm sure everyone has played with magnets, and you can feel that they don't want to go together, that as you push them, they push even harder against you. And if you let them go, they'll push away from each other. So two positive charges will behave in the exact same way, and so would two negative charges. So two negative charges would also experience a repulsive force. Now, a few videos from now, we'll look at how do you calculate what is the magnitude of this force. But for right now, it's enough for you to know that opposite charges attract, so a positive will attract a negative, and that two positives repel and two negatives repel each other. These are going to become important because as we explore charges more closely, we're going to want to test things out. I'm going to want to know, well, what is the charge on this thing? Is this thing a positively charged thing, or is this thing negatively charged? And we're going to use these rules as a way to establish what is the charge on this unknown object that we're not familiar with. Now, charges don't just exist like this. The charges actually, this positive or negative charge is something that is a property of the little tiny particles that make up matter. And when I say those little tiny particles, I'm not actually referring to atoms. So atoms themselves normally are neutral, and that is because they are composed of smaller particles that actually contain the charge. So atoms are essentially empty space, and they are tiny little particles that orbit around each other based on their mutual attraction, because you have positives and negative charges that are kind of drawing the thing together. So clearly the proton is the positively charged, and the neutron, which actually contains the root word of neutral, those are both positive and neutral, and they are in what's referred to as the nucleus. So that's the center of the atom, and that is where almost all of the mass, actually 99.9% of the mass, is in these particles. They are orbited by much smaller particles, which are negative, and as I just said, they orbit the nucleus. And I'm sure a lot of this is kind of reminder from middle school science classes, or from really any high school class. I'm sure you went over the basics of how atoms work. We could draw a little picture of an atom that is composed of little tiny particles in the nucleus. Now, these little tiny particles are constantly buzzing. They're kind of vibrating in place all the time, and then they are orbited by electrons. And just like the way satellites orbit, or in a very similar way to the way satellites orbit, they are attracted to the nucleus. There's an attractive force, but because they have velocity, that allows them to create this kind of stable situation. I'm not calling it equilibrium. It's not equilibrium, but it creates a stable situation where the electron can orbit like that essentially indefinitely, so long as it maintains its speed, just like the way the satellites, they don't fall and they don't escape so long as they maintain their speed. Okay, so that's like a little bit of review in terms of how the atoms look, but let's talk about how moving forward we're going to be able to communicate with each other about what the charges of things are. This piece of paper, for example, that I'm writing on is literally composed of trillions upon trillions upon trillions of little charged particles, electrons and protons. So if I wanted to draw, well, what's the charge on this piece of paper? That would be very difficult for me to do, because am I literally going to draw all the charges? You'd have to be able to see down to the level that they're at in order for me to do that. So it's not really feasible for us to draw all of the charges that are on objects. So we are going to use these conventions. And the word convention, if you're not familiar with it, the way I'm using the word is an established set of rules. So for example, in the United States, we drive on the right side of the road, and in the United Kingdom, they drive on the left side of the road. And everything is fine so long as we stay consistent with our system. So what I want to create is the conventions, I should say, for how we are going to draw charges. How can you show on a piece of paper what the charge on something is? So if we have neutral objects, which is oftentimes the way we're going to be starting, we'll do it one of two ways. So here is a larger pith ball. Okay, so I can either draw them with nothing inside of it. So if I draw something and I don't put any indication of charges, I don't put any positives, I don't put any negatives, then that object is neutral. Or I could actually draw charges, and all I have to do to make sure that I indicate that this object is a neutral object is I draw equal amounts of positives and negatives. If I draw two positives and two negatives, that's neutral. If I draw 10 positives and 10 negatives, that thing is neutral. That's going to be really important because there are going to be times where we're going to see movement of the charges inside of a neutral object, but it's still not charged. So somehow we have to have a way of indicating that the object is neutral, but that there is something happening inside of it. We're going to explore that in the coming up in one of the next videos, what happens inside of neutral objects. If objects are charged, then I will only draw the excess charge to indicate that something is charged. Indicate that something is charged. Okay, so what I'm saying is that I'm not saying that this only has positive charges. What I'm saying is that there's positives and negatives. All objects have both positives and negative charges. But what I'm saying is that there is an excess of positive charge. So the reason why this thing is positively charged is because there are more positive charges inside of this object than there are negative charges, and therefore there are extra positives. And so this object is going to behave as though it was a purely positively charged object because of that excess. And similarly for the negatively charged objects, it's not that there aren't positive objects in it, it's just that they are overwhelmed or that they are overpowered by the larger number of negative charges. So any object that is charged is because of the imbalance, and that's all we want to express. We don't want to draw all the charges because that's confusing. You know, what I could do is I could draw, like, let's say 5 positives and 2 negatives. So that would indicate that the object was positively charged, but then it seems unnecessarily complicated. You know, why would I draw any of the negatives when there are more positives than there are negatives? So it's just easier for us to indicate neutral objects versus charged objects, and then we're going to put this into practice in the very next video.